short introduction. Hi everyone, my name is Chen. I'm a third-year PhD student from UC San Diego. Today I'm glad to be here to present our work, You Only Render Once, Enhancing Energy and Computational Efficiency of Mobile Virtual Reality. This is a collaborative work between UC San Diego and the University of Colorado, Denver. So the mobile virtual reality includes systems like smartphone VR and standalone headsets such as the Meta Quest. This mobile device can create 3D virtual environment that provides immersive experience. In the past few years, the number of mobile VR users has gone quickly. Now almost 3 times more than PC VR user. However, mobile VR still faces big challenges, especially in rendering. Rendering VR content requires a lot of computing power. It can take almost twice as much as rendering a normal 2D video. Normal mobile VR can only last like 2 to 3 hours of usage. So this put a heavy load on mobile device and limits the experience. So most traditional optimization methods mainly focus on reducing the complexity of the rendering content, but it often comes with a cost. It can lower the graphic quality and hurt the visual details. There is an example when a PC game is ported to the mobile, the model details, textures, and visual effects are usually greatly reduced. But this trade-off helps us the game to run more smoothly, but it also lowers the visual quality. So one major source of the computation in VR is that each frame needs to be rendered twice, so basically once per eye. But if you look closely, most of the content, such as the pixel colors, is almost the same between 2 eyes, but only some slight difference to create a sense of depth. So the natural question is that, can we avoid rendering twice and save all that computation? To dig into this, we can first take a look how a single frame is rendered. First, the mobile app will provide the same information to the render. This includes some 3D mesh of the objects, the textures, material, lighting, and maybe some other post-processing effects. Then the render iterates through all the objects, basically all the triangles, and draws them on the screen. So this process is referred as the rasterization. During this rasterization step, the depth information is also calculated automatically because it will help to decide which pixel colors should appear in the front. Finally, the render output the color frame along with other information such as depth map and the surface normal. Here is an example of the depth map and the color map. This can be directly obtained from the G buffer, which is a part of the rendering output in most modern game engines. So here we propose you only render once for VR rendering, so or simply Euro. Unlike conventional methods that render 2 images per frame, Euro only render once, and then it can quickly predict the image for both sides. It's making it much more suitable for mobile VR. And it is important to know that this is a completely different task from the novel view synthesis. Those methods focus more on visual quality and usually rely on neural network or without considering the real-time performance or computational cost. Our method is based on reprojection. So this idea is somewhat similar to how LiDAR or depth camera generates the point cloud. But here we optimize it specifically for fast and efficient rendering on mobile device. And just to clarify, everything you see here on the slides all come from the virtual 3D scene, not real world data. And we are now trying to do some reconstruct scenes where we're using information from a rendered frame. So for each pixel in the rendering frame, we can obtain the screen space position, where the Z value is the depth. By multiplying each pixel with the inverse of the dominant eye, intrinsic and the extrinsic matrix, so that is the VP matrix here, we can recover some partial information of the 3D scene. You can see this example that here on the slide. Note we do not actually store those point clouds. This is just for illustration purpose. Then for each pixel, we can multiply it with the other eyes matrix to get its screen space position from another eye's perspective. These steps are all linear operations, so we can pre-compute the transformation matrix denoted as M, as shown here. This matrix asks us to map the left eye image to the right eye image, or vice versa. Importantly, this M matrix is computed once per frame, not per pixel. So the transformation becomes a simple matrix modification, which is much more easy to parallelize on mobile GPUs. So you might have noticed in the previous video the reprojected frame isn't perfect. Some regions appear to be black, and this happens because some pixels are from the right eye are getting mapped to the same pixel position as in the left eye, leaving some gaps. So we call this disocclusion regions. To improve visual quality, we need to patch or fill in those missing areas. This is similar to image impending task, but again, we cannot use any heavy algorithm or neural network here because our goal is to keep computation low and support real-time performance on mobile device. Our solution is to use image filter for patching, but unlike a traditional filter such as Gaussian or blocks filters, which often produce some blur results, we take different approach and that is tailored for mobile VR reprojection. Here are some interesting observations that we found specific to this task. First, all pixel displacement are horizontal. So instead of tracking 2D shapes, we can just use 1D value to represent the pixel movement. So this might sound like small, but for every saved operation matters when we are optimizing on GPU. Second, we observe that the disocclude region should only be filled with the background pixels, not the foreground one. So as shown in this example, the black region should be filled with the dark green color instead of the yellow foreground. We can use this kind of observation to guide the design of our custom filter. Here is an illustration about how our patching filter works. For each missing pixel, we only sample to the left since all pixels are displayed to the right during the reprojection. We also skip any foreground pixel inside of the kernel, so only sample from the background based on the depth. This might sound a little bit complicated, but it's actually quite simple and effective. You can find the full implementation in our code base. Here example of the input and output of our patcher filter. The input is reprojected depth image and color image, and the output should be the final frame without any disocclusion region. Euro is implemented directly on GPU using standard shader languages, so it's capable with any major game engine or graphic library, including Unity, Unreal, OpenGL, Vulkan. So it can be easily integrated into existing VR applications. We also focused on some performance optimization. So this pipeline uses half precision 14-point operation, and we carefully reduce any expensive memory access to maximize the speed on the mobile GPUs. So how do we actually make sure the algorithm work in practice? So we evaluate Euro from different perspectives because VR content can be very allowed in terms of scene complexity and artistic styles. To do this, we create 8 diverse virtual scenes for testing. As you can see here, they cover a wide range of styles. For example, the scene A, Bistro, is a realistic rendering of the street, and scene E is a Minecraft-style blocky environment designed for games. And scene H here shows a cartoon-style anime character. So we also tested on different kinds of mobile device. We choose 6 types of mobile phone, and also as well as the standalone mobile headsets such as the Meta Quest 2 and the Meta Quest 3. We first analyze the computational complexity. Both conventional method and Euro are linear in complexity, but they scale with the number of the triangles, or roughly the ON. But if we look at the actual time it takes, there are some key differences. For conventional rendering, time is about 2 times n, where n is related to the number of triangles. But for Euro, the time is close to n plus a constant, where here I refer as C. The C is mostly depends on the screen resolution, and it's much smaller than in real applications. So here in practice, Euro is nearly cut the rendering time in half. This is possible because both the reprojection and the patching step are done entirely in the screen space. They do not depend on any 3D geometry. To verify this, we run a benchmark where we aggressively increase the number of triangles in the scene. As the graph shows, the rendering time with Euro goes much more slowly, about 50% less than the conventional rendering, and is also faster than other baseline rendering methods. For each scene, we require the memory usage, frame rate, image quality, and battery consumption across different rendering methods, including Euro and the other baseline approach. Okay, since the bar plot can be a little bit boring, so I add a demo video on the side, so just keep seeing a little bit more entertaining. So across all tested scenes, Euro improves the frame rate by on average of over 115%, effectively doubling the frame rate compared to conventional rendering. Euro also can reduce the power consumption by around 27% on average, helping mobile devices run longer without overheating. Memory usage stays the same, even with a slight reduction, because we reduce some copying image frame buffers on the GPU side. We test Euro under different eye distance of the VR headsets from like 5 centimeter to 7.5 centimeter. Euro consistently produce high quality images showing like strong adaptability. We also run Euro in an hours-long pressure test, which also shows stable frame rate improvement. Euro also maintains high image quality across a wide range of rendering style, including realistic, voxel rendering, low polygon, and anime style, with a SSIM consistently above 0.95. And because thanks to our custom filter design based on the observation, based on all the observations which I showed earlier, Euro can even outperform a heavy image imprinting algorithm and neural network-based method, while being over 1,000 times faster. We also noticed that SSM and PSR, although they are widely used for image quality evaluation, they are not perfect. They mostly capture the overall image similarity, but they miss the visual difference, especially in those disoccluded region. So we conducted a user study with 14 participants. We showed them the scene rendered by different methods in a random order. For each scene, we asked 2 questions: which one they feel have the overall best experience, and which one they think has the best image quality. Then we ran 2 statistical analyses on their response. The results shows that Euro was constantly preferred for overall experience, and its image quality was statistically indistinguishable from conventional rendering. And you can find all of those detailed statistical analyses in our paper. To conclude, we introduced Euro, a novel rendering approach that only renders once per frame. It produces high-quality binocular image for VR. Second, Euro brings significant improvement. It cuts computation and power consumption, or doubling the frame rate in most cases. Finally, Euro is lightweight and production-ready. Means it can be plugged into existing VR app and run efficiently across a wide range of mobile devices. I'm glad to share that all the material in this paper, including the source code, demo video, demo app, and all results data are available online. We also provide a Unity game engine that is free to use. Please go to our website for more details. And thank you for your attention. I'm happy to take any questions.
Thank you, Xinyu. Yeah, please.
Thank you, Xinyu.
I'm Xingyu from Michigan State University. I think this is actually a very important topic. However, one thing that I found out that is you are rendering one frame with the input of one dominant frame. So there means there could be like a time difference in terms of the two frame.
No, there is no.
I mean, one frame is the output of the other frame, right? You did
Yes.
some transformation.
Yeah.
I mean, for human eyes, a slight like temporal difference can cause some dizziness. That's the thing that I'm concerned. Yeah.
Yeah, sure. Because the rasterization currently use double buffer rendering, so they will render the next frame completely before showing it on the headset. So we're actually rendering two frames and switching to buffers. So there is no latency in those.
So two eyes will see the
Yes.
same situation at the same time. Okay, even though one is the
Yes.
after effect of the others.
Yes, and we can achieve more than 120 frames per second.
Okay, and what's your like improvement in terms of the latency? I mean, theoretical limits will be like because you just use one frame will be just 2x, right?
Yeah.
Okay, how close are you?
We actually we found that our improvement is actually beyond those theoretical
How is
model.
that possible? Because you just
We actually debug into this. We found out when the mobile app are rendering 2i, there are a lot of memory copying or image buffer copying. So if we only render one eye, we can avoid this buffer copying, so it can save us more time.
Okay. Thank you. Hope to see more of your work.
Okay. Thank you.
Thank you so much.